It's okay? Yes. So welcome to the second session of this afternoon. We will have two talks, one live, one recorded. So the first one is live, as you can see, and it's even the best paper award of this event. So congratulations again.
Thank you.
So, and it's given by Barbara.
Thank you, Nicolas, for the introduction. Hi, everyone. My name is Barbara, and today we dive deep together in the question how to reduce the number in solving, how to reduce the number of qubits in solving LWE. As all of you know, and probably we heard it a couple of times on this stage at this conference, LWE is hard to believe to solve. It's a lattice problem which is even hard to solve for quantum computers. LWE was originally proposed by Regev in 2009 as a public key encryption scheme. Given is a matrix A and a vector B as a public key. And the LWE problem asks to solve a linear equation B equals to AS. So S is the solution of this linear equation, which is disturbed by a small error vector E. However, this LWE problem is very relevant in post-quantum cryptography and in dilithium in the general form as you can see it here. However, in my talk, we're going to look into a special setting of the LWE problem, the ternary LWE problem, meaning that the vectors S and E are both ternary, so every entry is either 0 or plus minus 1. And we also assume that there is a further parameter given, W, which gives us the number of plus 1 and minus 1 entries of the solution vector S. How can we solve this ternary LWE equation? It turns out there exist quite a few LWE solvers in this setting. If we draw all these solvers in this figure, we can see that they have different requirements in classical memory, in qubits, number of qubits they need, and also they have a different runtime. On the very right of the figure, you see a gray bubble, which is May's purely classical algorithm. Next to the gray bubble, you see a black bubble. This is kind of May's classical algorithm, but combined with as many qubits as you need to run a quantum random walk. And the resulting algorithm runs faster than the gray one. On the very left of the figure, you see a green line, which is much slower, but requires less memory and only linear many qubits, compared to the other both algorithms. Is there something you can see when you look at this figure? For me, it is very obvious that when we look at this figure, that there's a huge gap in the middle. And I asked myself, is there something what we can do? Are there LWE solvers which exist in the middle? And in my paper, I investigate in this question and propose a new LWE solver, which is filling the gap in between. And it's also worth to mention that my new ternary LWE solver allows the treasury to adapt the memory requirement. So assume you have memory given, which is somewhere in the middle of the x-axis, so somewhere located here, meaning that you don't have enough memory to run one of the algorithms you can see on my left side or on your right side of me. And you only can run the algorithm which is represented by the green line. However, now with a new ternary LWE solver, you have the possibility to have a much faster LWE solver. And what is behind this green algorithm I want to introduce to you? To answer this question, it is better to have another picture in mind, a picture of a puzzle. This is because the main contribution of my work is that I gather all these puzzle pieces and fit them together to a new ternary LWE solver. And this is also what I want to do for the rest of my talk. We will take a closer look into each of this puzzle piece and look what is behind it, and then get an overview about the new LWE solver. So what is behind Mai's algorithm? Mai's algorithm is a purely classical approach following a meet-in-the-middle approach. This means that Mai takes this LWE equation you've seen before and splits the solution S into two parts, S1 and S2, and then rewrite the equation by putting S1 on the left-hand side of the equation and S2 on the right-hand side of the equation. And then on a high level, Mai's algorithm does this. It samples candidates for S1 and S2 in a way I don't want to specify in my talk. And then there is like a cloud in the middle that matches candidates for S1 and S2 and looks for pairs where both sides of the reshaped equation matches and filters for the LWE key. As I said, this algorithm is purely classical. So how can we combine this into a quantum algorithm? Therefore, we need to take a look on the second puzzle piece, the CNS algorithm. This is an efficient algorithm which you can use to find collisions. And if we go back to this picture, we actually can use this algorithm. We really can combine Mai's algorithm and the CNS algorithm, since the cloud in the middle is essentially doing a collision search. So having the reshaped equation in mind, it looks for a collision S1, S2, where like both sides of the equation are colliding. So we can change the picture to that. So what does the CNS algorithm do now? As before, we would sample candidates for S1 in a classical way, meaning we just sample them and store them in a list. So left side remains classical as before, and the quantum magic just happens here on the right side. The second part of the solution, S2, we will search in superposition for this. How do we do that? Searching in superposition means it's just another word for doing a Grover search, or generally spoken, to do an amplitude amplification. And to understand it in a better way, how we can combine amplitude amplification with the LWE solver, we need to take a step back and go to that picture. Remember that we are not looking at the general ternary LWE problem. We have this further parameter W given. So this was the number of +1 and -1 entries of S. And so far, I also didn't tell you how Mai is sampling candidates for S1 and S2. But what is now important to mention is that in his algorithm, S1 and S2 have also specified numbers of +1 and -1 entries. And indeed, it makes a difference for amplitude amplification if we already know the weights. So assume we want to use amplitude amplification to search for S2, and we do not know the weight W2. This means that we would start with a uniform superposition over all vectors, and then amplify the amplitude of this solution we are looking for. And we need some iterations until we have a good probability that if we would measure this state, we indeed get the solution S2. However, if we know W2, we can narrow down the set of relevant elements. So in that case, we do not need to start with all 4 elements, but just can start with 2 elements. And this means that we can decrease the number of iterations which are needed, and this actually saves time. The only question which remains now is, how do we get this initial state if we have weights given? And to answer this question, we need to take a look on the first piece of the puzzle, the one about generalized Dicker states, which is like the second main contribution in my paper, where I propose an algorithm how you can prepare them. Generally spoken, a Dicker state, I use that notation, it's d to the n of w, is an equal superposition of n-dimensional binary vectors with weight w. This sounds complicated, but in a very simple example, so this is a Dicker state with weight 1, and n is equals to 3. So we have a 3-dimensional Dicker state with weight 3. It looks like this. And there exists an algorithm how you can prepare them by Berthian eigenbands. And the main thing is that the Dicker states are about binary vectors, but since we are interested in the ternary LWE, the states which are interesting for us are the ternary states. And therefore, we need to look in the generalized Dicker states. In general, they can have like another underlying set than 0 and 1. And for us, in particular, the ternary vectors are interesting. So this, for example, could look like this. This is a picture of a 3-dimensional Dicker state where the weights are 1, 1. So we have vectors where we have 1 time the entry 1 and 1 time the entry -1. And in my paper, I give an algorithm how you can prepare these Dicker states, also requiring linear time as the one of Berthian eigenbands, and at most using linear many angular qubits. Having an algorithm how you can prepare ternary Dicker states, we actually can complete this picture. We can use the Dicker state of dimension n with weights, which we need to choose in dependence of W2 as an initial state for amplitude amplification. What allows us to apply CNS algorithm on Mai's algorithm so that we get the LWE key S in the end. So as I said, this completes the picture, so we can leave LWE behind us. And the rest of my talk I want to spend on the question how we can prepare generalized Dicker states. And to give you an idea how to prepare them, we need to do 3 observations. The first one is that Dicker states have an inductive structure. Therefore, we look into a simple example, so 3-dimensional Dicker states with weight 1, 1, which looks like this. And if you take a closer look, you see that there are 6 vectors. So we have a uniform distribution over 6 vectors. And each 2 of them have the number 0 in the last entry. Other 2 of them have the entry 1 in the last entry. So that we can divide this Dicker state by the last entry, what looks like this. What makes it obvious that having a 3-dimensional Dicker state on the left side, we can divide it in 3 different Dicker states of dimension 2. And now the picture is only missing like the right scaling of the probabilities of the right amplitude, which I add now on the picture. So we have the Dicker states scaled by the square root of the probability that we get in this specific case. So in that case, it's 2/6, since for 2 of the 6 vectors, we have a specific number as the last entry. When we want to benefit from this inductive structure and to construct our algorithm, we need somehow a procedure how we can divide the task of building a Dicker state of some dimension into subtasks where we want to prepare Dicker states of a lower dimension. And this leads me to my second observation, that we can achieve this dividing into subtasks by swapping the entries of the vector. Again, I want to tell you what I mean by this by a simple example. So assume we want to prepare a 4-dimensional Dicker state this time with 2 times 1 entry and 1 time a -1 entry. Then we would start for the algorithm with a pure state. So this means if we measure this state, we will get with probability 1 this vector 0, 1, 1, -1. The important thing is that this vector already has the correct weight. And somehow we want to translate it in 3 subtasks, like of the same form, but of a lower dimension. So we have there a 4-dimensional pure state, and we want to transfer it to the right side with 3-dimensional pure states. I think it's getting more understandable if we start to translate it. So the first thing what we do is we take the probability and divide it in as many parts as the dimension of the Dicker state is. So in that case, just in 4 parts. And now we take 3 of the 4 parts. And for these 3 of the 4 parts, we switch the 3rd with the 4th entry and draw this in the right side. Now I use different colors to show you which of the parts we actually swapped and which not. So the part which we haven't swapped, it's the one with a -1 in the last entry. We changed the color to blue. and the other 3 parts remain, are still green. The second step is again now to swap entries of the vectors, now the second and the fourth. And we do this for 2 of the 3 green parts. And in that case, the second and the third entry have the same number. So swapping doesn't really change something. It just changes the color of one part. And the last step is again taking one part of the 2 green parts, swapping what changes the picture to this. And actually, if we are doing the procedure like this, we do not take any more, we don't need to take care of the scaling, because as you see, we start with something where we had 2 times the entry 1. And now we have here, by doing this procedure, that the probability that we're coming in that case is also twice as high as in the other cases. How can we implement this on a quantum computer? This leads me to my final observation, that we actually can implement all this logic behind the swapping in Ancilla qubits. So we use the rotation gates in the green box to swap with the correct amplitude. And we use the controlled XOR gates to make sure that we do not swap the blue parts anymore. Okay, this was just a very quick overview how we can prepare the sticker states. To wrap it up, we looked behind every puzzle piece. We have got an overview about the ternary LWE solver. Especially, we looked how we can prepare the sticker states. And if you find that interesting, I would like to invite you to scan these both QR codes. Then you can find a Qiskit implementation and also a web page or a circuit implemented in Quark where you can where you can play around with the circuits. Okay, this concludes my talk, and thank you for listening.
Thank you, Barbara, for this excellent talk. Do we have questions? Okay, there.
Yes, thank you for your presentation. What about other moduli? Is there something special about ternary LWE, or do the results generalize to other moduli?
So the algorithm also works if you don't have a ternary solution. What is important is that you somehow need to know how your solution looks like. So in my paper, you can find algorithm how you can prepare the generalized sticker states, also for higher dimension, not only for ternary vectors, but it's important that you know how many times the vector has the entry 2, for example. So in theory, it's applicable, and maybe you also can guess how your LWE solution might look like, but I'm not sure how the runtime is. Probably not too good.
Well, I have one question. This kind of state appears also in the generic decoding technique that is used for code-based cryptography to evaluate the hardness of decoding. Mm-hmm. And you probably have the same kind of sampling problem of constructing states with constant weight words. Did you have a look at that? Can your technique improve something?
I took a look at that. They are only using like the binary, the usual Dicker states. I'm not an expert in code-based cryptography, but I assume that there you also have like more advanced algorithms where you're using more representations and also have this ternary vectors. So I guess you somehow could combine this, but I didn't take a look at that.
Okay. Anything else? Okay, so thank you again.